Okay, good morning, everyone. So today we still continue our discussion in fluid and particle mechanics class. It's still about the energy loss due to the friction. And now we will discuss in details regarding how to quantify the friction caused by the fitting. And one of the types of the fitting is valve. I think from the previous video, you can see that in pipeline system, in chemical plants later, if you have chance to visit chemical plants, hopefully, you may find several types of valves as explained in the video. Yeah. And what can you see from the video? What will be the differences between each valve? Why each valve has a different name? Or what will be the different function between each valve? I think in general, what is the difference? Raha dan Neswara.
Yes, sir. I think it's about the shape also, sir. Like they have the globe valve that looks like globe, and then gate what gate valve that looks like gate. Gitu. Jadi depends on the shape and the function, so the name is different.
Okay, actually the different names of the valves is correct. Yeah, it comes from the shape representation, or sometimes the name is also comes from the function. But if you see the video from the beginning, you may found that the function of the valves generally are first is to what? Start and stop the flow. Yeah, some valve is only function to start, either start or and stop the flow. Yeah, the second one, some other valves can also be function as for controlling the flow rate, or in this video they use the term throttling. Yeah, it means this kind of valves can be used to adjust the flow rate. And besides the differences in the shape, yeah, actually you may see, because when you watch the video, when each of the valve, the mechanism of each of the valve is explained, you can see the internal, right? The internal from the internals of the valve, and you may see that the disc type is different. Yeah, the shape of this disc is different. The butterfly valve, the disc looks like butterfly. The ball valve, the disc is like a ball, and etc. So this mechanism, the differences in the internal structure of the valve, and also the differences in mechanism in when the disc, or the one inside the valve that later can be closed or open, it may influence the flow pattern of the fluid. Yeah, when the fluid, for example, if you have water previously flowing smoothly inside the straight pipeline, and then in the middle of the journey, then this water encounter one type of the valve, maybe a disc valve or globe valve. So you can see, right, the length of the valve is quite short. But since the internal structure of the valve, especially when the gate or the disc is in some position, right? Because at the short length, the fluid will go to the valve, will go inside the valve, and they will change the flow pattern. Yeah, the flow pattern in a very short time. So the change of flow patterns will increase the loss of energy contained in the liquid or in the fluid. Yeah, so basically by adding valves or other types of fitting we have discussed. Yeah, fitting is not only valve, but it will yeah, I'll show you the figure. Yeah, it can be in form of valve, it can be in the form of maybe T, or maybe elbow, or maybe diffuser, or maybe sudden contraction, and or maybe strainer, and other oh, it always goes, sorry. how to stop the video. Yeah, so it can also in the form of different types of valve. So each time the liquid is flowing inside the fitting, they may change the flow pattern, and change of flow pattern will create energy loss. Now, how to quantify and or how to calculate the energy loss? So basically, the energy loss due to fitting installation can be modeled as friction energy loss. Ya, jadi energi yang hilang akibat pemasangan fitting itu kan sebetulnya muncul karena perubahan pola aliran. Nah, kuantifikasinya atau perhitungannya itu sebetulnya bisa dimodelkan atau disamakan atau dimiripkan ya fenomenanya dengan energi yang hilang akibat friksi. But this one is more into the change of flow pattern. Yeah. How to calculate the friction loss or the energy loss in fitting? First, it can be calculated in two ways. First, by calculating what we call equivalent length. Yeah. So in this calculation, we calculate the friction loss by defining the equivalent length. What does it mean by the equivalent length? For example, you have a gate valve. Yeah, gate valve with the diameter of 3 inches, and then it fully open, for example. Yeah. So previously, like this, right? So this is the valve. Yeah, this is the diameter. Yeah, with the diameters. The gate valve, the length of the valve, it's maybe only like 15 centimeters. Yeah, when the liquid or the gas are flowing, yeah, since the gate valves will create energy loss due to the flow pattern change, you may find that the pressure from the inlet with the pressure of the outlet of the gate valve is different, right? So since you have energy loss, you will have pressure different or pressure loss in the gate valve. How to define the equivalent length? This pressure loss, yeah, this same amount of pressure loss also can be created if you flow the same liquid, yeah, the same liquid into this the pipe with the same diameter. So it's like 3 inches, but different length. Yeah, in the straight pipe, the pressure loss will be occurred due to the friction between the wall. However, the same amount of pressure loss maybe can be obtained when you flow the same fluid in the maybe 1 meter of straight pipeline. So with the 15 centimeters of gate valve with fully open, and then you flow the liquid, yeah, you can obtain the same pressure difference if the fluid is flowing through the 1 meters of straight pipeline with the same diameters. So it can be said that the equivalent length of this gate valve will be 1 meter. Yeah, so the equivalent length is basically the length of straight pipeline, yeah, that will create equivalent or the same amount of pressure drop with the fitting. Ya, jadi yang namanya panjang ekuivalen itu adalah panjang dari pipa lurus yang akan memberikan pressure drop yang sama dengan fitting tadi. Of course, it should be in the same diameters. So the equivalent length of this gate valve is not 15 centimeters, but it will be 1 meters. How to get the value? 15 centimeters and 1 meters is only example. But how to get the value? Of course, you need to take measure of the pressure of the gate valve, yeah, in the inlet and the outlet. Then you can get the delta P, And then you also have to take measure of the pressure of the straight pipeline. So how long is the pipeline? That's finally will give the same pressure drop. That's you call the equivalent length. So if you have the equivalent length of the fitting, then you can just use the same equation, yeah, AF. Please remember, yeah, this is the formula to calculate pressure loss. So this will AF. And please take note, just correct this one, delete this one. So if you have the value of the equivalent length, to calculate EF is just use, you can use the same equation for EF calculation for the straight pipeline, but you must use the equivalent length. Can be understood, right? So in this method, you calculate EF by knowing, or you have to know first the value of the fitting's equivalent length. Yeah, the procedure is the same. You find the velocity first. Yeah, you find the velocity first, and then you calculate the Reynolds number, whether it's in the laminar or turbulent, and then you calculate the friction factor. Don't forget, you still need to include the friction factor. Yeah, you still need to calculate the friction factor if the fitting is in the equivalent length. Don't forget again, what is the unit if you calculate using this formula? EF will be in joule per kilogram. Yeah, specific energy or energy, energy per mass. Yeah, this one you need to still remember. If you want to do the calculation, use the consistent unit. For example, if you are using the standard unit, like for the velocity is meter per second, diameter is meters, and then the length is also in meters. Yeah, so finally you will get the EF value as joule per kilogram. And later, when you want to put it into the Bernoulli, you have to make sure again that all the component in the Bernoulli should be in the energy per mass unit, should be in the specific energy unit. Yeah, this is the first method to calculate the EF from the fitting. Yeah, from this calculation you will get the friction loss with the unit of energy per mass for the fitting by knowing the equivalent length. The second method is to calculate. So in this second method is basically you correlate. Just a minute, somebody call me. Yeah, so for this second method, the friction loss, yeah, EF, yeah, EF is basically you can calculate EF by defining what we call fitting constant atau konstanta fitting. So that this fitting constant is correlating the EF, yeah, with the kinetic energy. Yeah, so because we can imagine that the pressure drop due to the fitting installation, it can be correlated to the loss of the energy, yeah, to the loss of energy, and one form of the energy is the kinetic energy. So in this one, it's basically you do not need to find out the equivalent length, you do not need to find out the friction factor, yeah, but what you do in the experiment is you calculate delta P, yeah, this is the P inlet, this is P outlet, yeah, you will have delta P, right, due to the fitting, and then you variate the flow rate. If you have pipeline with the certain diameters, yeah, for example, like 3 inch, then you variate the flow rate, you can variate velocity, right? Because velocity is flow rate divided by the area. Yeah, you variate the velocity, and then you take note, you measure what will be the pressure drop. So you correlate, you put it into the graph, you will get linear correlation between delta P over rho over density with the half of square velocity. Then you have the gradient, you will get the fitting constant. So this is how you get the fitting constant for each fitting using experiment, from the experiment. Yeah, for this one, if you already know the value of the fitting constant, yeah, if you already know the value of the fitting constant, then you just multiply the fitting constant with this value, yeah. Multiply the fitting constant with the velocity square, half of the velocity square, then you will get EF. So a bit different, yeah. For this one, you do not need to find out the equivalent length. You do not need to find out the Reynolds number. You do not need to find out the friction factor. You just use the constant of the fitting constant, then you get the EF. By this correlation, then you can see that KL or fitting constant will equals this one. And equivalent length will equals this one. Yeah, any question so far? So you can measure EF, yeah, by two methods. First, by knowing the equivalent length. If you know, if the data that you have is the equivalent length, the calculation step will be the same as the calculation of EF from straight pipeline. But if you have the value of the fitting constant, you can directly calculate the EF. Yeah, pretty straightforward, right? It should be simple. Okay, this is the value of some fitting. Yeah, sum of the fitting constant from some fitting. Yeah, you can see from the elbow with the same length, same degree of turn, but different connection. Yeah, flat is like welded. Yeah, threaded is like connected with the thread. It will give different KL. Also, if you have a globe valve with angle valve, with gate valve, 100% means it's fully open. Yeah, it will give different KL. Also, gate valve, but with fully open, with half open, with quarter open, it also give different fitting constant. It means how full the valve will be open will be different, right? And it will give different flow pattern. Different flow pattern will give different energy loss. Okay, now I'll go back from to this one. From this equation, yeah, from this equation, if you have two different fitting and one fitting have higher fitting constant compared to the other, what does it mean? Suatu fitting yang memiliki konstanta fitting yang lebih besar daripada yang lain artinya apa? Like this one. If globe valve have KL value of 10 compared to angle valve, what does it mean?
It produces a higher pressure drop for the same velocity.
Yeah, correct. So fitting with higher constant will have higher EF, yeah. For the same velocity, yeah, same velocity, if fitting constant is higher, it means EF will be higher. It means delta P will also higher. This fitting will create higher pressure drop. That's why in this video, I think if you listen carefully, some types of valve will have lower pressure drop, but other types will have higher pressure drop. Against this, because of the change of the flow pattern when the liquid is flowing inside. Generally, if the liquid experience more rapid flow pattern change or more extreme flow pattern change, then the energy loss or EF or pressure drop will be higher. Okay, any question? Okay, if you do not have any question, then I'll show you what will be the meanings of the fitting constant. Is basically, fitting constant is correlated to the change of the flow pattern, right? And the change of the flow pattern is basically comes from change of the geometry inside the fitting. Yeah, you still remember for the sudden enlargement. Sudden enlargement will have higher diameter on the outlet. Because it has higher diameter, at the outlet will have lower linear velocity and higher pressure. Yeah. Then let's try to imagine you still remember Bernoulli equation, right? But this Bernoulli equation, you compare between inlet of the fitting, inlet of the sudden enlargement, and the outlet of the fitting. Yeah, 1 KZ2 plus KZ2 plus half of the quadrant. Because the position is horizontal, then the potential energy can be neglected. Yeah, so from this equation, you can formulate how to calculate EF. EF here represents pressure represent friction loss of the sudden enlargement. It will be influenced by the pressure drop and the velocity change. Okay, from the continuity equation, yeah, when the mass flow is always constant, mass flow rate is always constant, then you can correlate the outlet velocity as the function of the inlet velocity using the size comparison, the size ratio, the diameter ratio. So you will get this equation. Yeah, and then we can define, this is just the constant to correlate the EF, yeah. So if we put this constant, yeah, P2 minus P1 divided by half times density times U1 square, then you will have EF equation into this one, and you will have this part is the fitting constant. Okay, by deriving the fitting constant equation, you can see, right, the fitting constant will be influenced by the size of the diameter, the ratio of the diameter. It means it will be influenced by the geometry of the sudden enlargement. Although in CP, it may also be influenced by the pressure drop. So from this derivation is basically just to show you why the fitting equation, why the fitting constant is influenced by the geometry of the fitting. Yeah, you can see, right, from this one, it will be influenced by the diameter ratio, and then you can correlate the fitting constant as the function of the AR. AR is this one, D1 divided by D2 to the power of 4. Okay, some experiment. This actually comes from the experiment. When you increase the AR, yeah, AR is this one, yeah, D1 divided by D2, yeah, AR is D1 divided by D2, this one. When you increase the ratio, yeah, the fitting constant is decreased, yeah. So if there is no difference between diameter 1 and 2, it means AR is 1. So the fitting constant become 0. Because what? Because if you have, this is the example, the fittings example is the sudden enlargement. So if the fitting constant, if the AR is 1, it means it's no longer sudden enlargement, right? Because D1 equals D2, it becomes just short pipe, short straight pipeline, pipe, yeah. It means you will have 0 fitting constant. there won't be any pressure drop in the short straight pipe. But if you decrease the AR, it means the differences between each value is larger, is higher, then you will have higher fitting constant. This one is always 0, right? Because it means you don't have, I think this one can be neglected. D1 divided by D2 equals 0 means there is no fitting. Okay, any question until this part? Okay, if you have no question, then I want you to imagine this situation. Yeah, you have two segments of pipeline. Yeah, now we want to evaluate the value of the pressure drop when the fluid flowing into some complex pipeline system. So in this example, you will have two segments of pipeline. Between these two segments, they will have a different diameter. So in segment 1, you will have segments of straight pipes with the diameter of D1. And then in this segment, you will also have several fittings with also the diameters the same, D1. So the total pressure drop or total pressure loss from this pipeline, yeah, this is the total pressure drop, the pressure loss, will be the total pressure loss from the pipe and from the fitting. Yeah. So if you have N1 segment of pipeline, then you will have this one is the EF calculation from length or equivalent length. Yeah, because from the straight pipe you will have the value of the length, and if the pipeline, if the fitting, the information from the fitting is in terms of equivalent length, then you do the calculation of EF using this equation. For some fitting, when the information is in terms of fitting constant, then this one. Then you just add those types of EF. Yeah. So basically the calculation is just like that. You calculate EF from the straight pipe and from the fitting. The same method is applied if you have the second segment, where the second segment have different diameter, D2. So you just calculate EF in the segment 2 from the straight pipeline and from the fitting using the second diameters. Okay, any question from this one? So you just calculate each EF, yeah, from segment 1 with the same diameters and from the segment 2 with the other diameters, then you get the value of EF from each segment. But don't forget, when these two segments will be combined, yeah, you have first segment with the D1 and the second segment with D2. So if you want to connect segment 1 to segment 2, you need additional fitting, right? For example, if you want to connect a smaller to higher diameter, then you need sudden enlargement, for example. Or maybe if the condition is inverse, you need sudden, what is the, yeah, you need the sudden contraction, yeah. So this sudden enlargement or sudden contraction will also create EF, right? Create friction loss. So EF from the connection should be calculated as well. Yeah, it can be in terms of KL or in terms of, actually you can also calculate it from equivalent length if the information is using the equivalent length. But for this one, please be careful. If you have fitting with different diameters between the inlet and the outlet, you need to use the inlet diameters to calculate the velocity, and then to calculate the Reynolds number, and then to calculate the friction factor. Yeah, please be careful about this connection one. For this one, it's pretty straightforward, yeah, because each segment have different diameters, so should be no problem. In segment 1, you are using D1. In segment 2, you are using D2. But for the connection, yeah, because you have diameter change, use inlet diameters to calculate the EF for the connection. So total friction loss or friction heat should be the total, should be the EF from the segment 1, from the segment 2, and from the connection. Okay, and then if you want to find the pressure drop, yeah, or pressure difference between inlet means the beginning of the segment 1, and outlet is the end of the segment 2, then you just put it into the Bernoulli. Yeah, 1 is 0.1, inlet of segment 1. 0.2 is outlet of segment 2. So beginning to the end. Just remember again, the Bernoulli equation is just comparing 2 points, right? 2 points. Yeah, but in this Bernoulli, you must include the EF. EF is the total friction loss from segment 1, segment 2, and from the connection. Okay, any question until this part? Ini diam saja, semoga mengerti ya, bukan bingung. Okay, now we see how about the complex piping system. Complex piping system is basically not just one pipe, one straight pipeline, yeah, but maybe pipelines can be branched into several other pipes. Yeah, one pipe is branched into more than one, and then maybe the angle, the height of the pipeline is different. Yeah, so for the complex piping system, you must still remember the concept of mass conservation. Yeah, the principle of mass conservation is still applied. So basically, when you have fluid, yeah, flowing into pipeline, just remember that mass flow rate at the inlet should be the same as mass flow rate at the outlet. If you have constant density, yeah, and then volumetric flow rate of the inlet should be the same as volumetric flow rate of the outlet. Yeah, this one you have to still remember. So if you have like branch, you have branch like this one, yeah, this one. Branch 4 is basically combining from branch 3 and branch 2. So the total of the mass flow rate at point 4, yeah, segment 4, is the total from segment 2 plus segment 3. Also, if you want to do the energy balance equation, yeah, energy balance equation is the Bernoulli equation for any pipe segment, yeah, any pipe segment with the diameter, with the certain diameter value and certain length value. So basically, you just calculate using the Bernoulli. Just remember, you always have to put it into specific energy equation. This one, right? For any point, any 2 points. However, if you have constant diameters, basically you won't get, you can neglect the kinetic energy change, right? So for this one, you can take down the velocity part, the kinetic part. However, the velocity value, you need to still calculate the velocity value in order to find EF. That's why in this final equation, you do not see the kinetic energy component. Okay, any question? Okay, if you have no question, then the same principle is also applies on different types of pipe segment. For this one, yeah, this is the inlet, this is the outlet, yeah, and then you have 1, 2, 3, 4, 5 segment. Yeah, if you have 5 segment, I don't know why this one is 8. Yeah, so the principle of mass conservation still apply. So the mass flow rate at segment 1 should be the same as segment 2, segment 3, segment 4, and segment 8. The last one is segment 8. How about the pressure drop? So if you want to calculate, I will bit corrected this equation there. The differences between pressure in the inlet and the pressure at the outlet should be PI minus PA plus PA minus PC, yeah, from segment 2, plus PC minus PD from the segment 3, and then plus PD minus PB from the segment 4 should be plus PB minus P outlet. Yeah, just correct the slide. But actually it's pretty simple, yeah. The concept is pretty simple. The pressure drop between the beginning and between the end is basically the total of the pressure drop of each segment. Because you have 5 segments, then this will be the total, yeah. This is from the segment 1, segment 2, segment 1, segment 2, 3, 4, and 8. Okay. Also, if you have this kind of pipe arrangement, yeah, when at point A, yeah, it's segment 1, at point A, the pipe is branched into segment 2 and segment 5. Yeah, and then at segment 4 and segment 7, the pipe is combined again. So for this, from this arrangement, you can see, yeah, from point A and point B, yeah, the pressure drop from point A to point B is basically can be calculated from the top part and also from the down part. Yeah, from the top part, this one, yeah, PA minus PC plus PC minus PD plus PD minus PB from the top part should be the same as the down part, PA minus PE plus PE minus PF plus PF minus PB. Should be the same, yeah? Because if not the same, then the flow cannot be combined at point B. Some will be flows back to the one that the pressure drop is lower. Yeah. Okay. From the mass balance, it's also should be still applied. Yeah. So at from the segment 1, it will be divided, right, in point A into the segment 2 and segment 5. So it should be like this. So this one should be equals, ya. Banyak koreksi ya di slide ini, jadi tolong diperhatikan baik-baik. So M2 should be the same as M3, should be the same as M4. And then M5 should be the same as M6, should be the same as M7. Will M2, is it the same as M5? Sama nggak?
Depends on the split ratio.
Depends on what?
The split ratio.
Yeah, it will depends on the split ratio, or it will depends on the size of the pipe in segment 2 and segment 5. If you have the same size, the same diameter between segment 2 and the segment 5, then it will apply. But this, if the pipes between the segment 2 and 5 is different, so will be different. Okay, any question? And then the total drop, yeah, should be like this, yeah. P inlet minus P outlet should be P1 minus PI minus pi A plus PA minus PB plus PB minus P outlet. Okay, any question? If you have, if you need further explanation, just speak up, yeah. Just open your mic and ask. But I think it should be easy, right? So it will be depending on the arrangement of the pipeline system. Okay, now we can try to do the exercise. Yeah. So you have this kind of arrangement. Yeah. First, at point A, this is water, right? Water with flowing in segment 1 until point B. And then at point B, the water is split up into segment 2 and segment 3. Water in segment 2 will fill the tank at point D. The tank is open to air. And also water at point 3 will fill the tank in point C. It's also open to air. Okay, you can see the size, yeah, the specification of each pipe in each segment. Yeah, you have the value, this one. Just be careful with the unit. Okay, and then water will flows in the system. Yeah. In segment 1, the flow rate is this one. So the flow rate at segment 1 is this one. Okay, and then the position, yeah, the head position or the elevation of each point you can see from this table. So as the baseline is point A, the elevation is 0, and then B is higher, and then D is higher, and then C is the highest. Okay, now the first question. What will be the flow rate at segment 2 and segment 3? If you were asked the flow rate at segment 2 and segment 3 by analyzing the table on the left bottom, what can you say about the flow rate?
Is it the same?
Why?
Because the diameters are the same.
Okay, so how much is the flow rate of each segment?
70 liters per minute.
Yeah, it should be half of the flow rate from the segment 1. Okay, can somebody help me to convert it into standard unit? How much is 140? So V2 should be the same as V3, should be the same as half. Yeah. How much is it in cubic meters per second? Please do the quick calculation. I'm waiting.
.0023, sir.
Can you note as sekian, koma sekian kali 10 pangkat sekian?
Okay. 2.3 times 10 to the power of -3.
For the V1?
Yes.
This one, right? Okay, so this one should be half of this one. Okay, for the others, please recheck the numbers. Okay, now you have the value of flow rate at point 2 and point 3. The next question is, how much is the pressure at point B? Yeah, point B, how much is the pressure? If you know the value of point A's pressure is this one. PSIG, still remember, right? 60 pound per square inch gauge. So for the Bernoulli equation, you always use absolute pressure. So please convert it into Pascal. Don't forget to add atmospheric pressure in this one. Atmospheric pressure is, this one is atmospheric pressure, right? So this one. Don't forget the number of atmospheric pressure. Yeah, it's if it's not known, you can assume it as 1 atm. So 1 atm is around 1.101.325 Pascal. Okay, can you calculate PA? In terms of absolute pressure in Pascal. How much?
I got 5.15 times 10 to the power of 5 Pascal.
5.45.
15.
Okay, this is PA, right? Then how to
15, sir,
calculate?
sorry.
Sorry?
5.15.
5.15. Okay. This is PA. How to calculate PB then? What kind of equation that you need to use?
Bernoulli, sir?
Okay, Bernoulli, between which point? You need 2 points, right?
A and B, I guess.
Okay, why you choose A and B?
Well, we know the velocity for both of them, and we know the elevation. So
Okay.
we can just solve for B, I guess.
Yeah, okay. Yeah, correct. You choose point A and point B. What happened if you choose point B and point C, for example? Or point, because you already know the velocity as well, right? The flow rate at segment 2 and the flow rate at segment 3 is known. The pressure at point C and pressure at point D is also known. What will be the challenge if you choose point B and point C, for example, or point B and point D?
More pipe segments.
More pipe segment. You just use one. Oh, you just use one segment, right? Either it's segment 3 or segment 2.
Oh.
Should be the same, right? Yeah. Actually, you can use point A and point B in the Bernoulli using segment 1, or point B and point C, or point B and point D. It's up to you. Should all calculation should resulted in the same value. You just compare. For example, if you want to use segment 1, so basically this one, right? Oh, I'll write this one. PA over rho plus GZA plus half minus EF will be PB over rho plus GZB plus this one. U1, yeah, because you are still in the segment 1. So the velocity is same, right? Because the diameter is the same. Your problem now is only this one should be 0, all parameters are known, and then your problem now is to calculate EF. How to calculate EF? First, from V1, yeah, you have to convert it into V1. Sorry, no dot. From this one, then you have to convert it into Reynolds number. From Reynolds number, you have to convert it into friction factor, and you have to convert it into EF. It's pretty straightforward, right? Just remember again, depending on the Reynolds number, whether you need to use the graph, yeah, or you need to use the calculation. If it falls into the laminar, then you just use the 16 over Reynolds number. If it falls into the turbulent, what other information that you need? Since you need to read the graph, right? What do you need? That might not available in this data. If you want to get the value of the friction factor using the fanning diagram, yeah, in the Reynolds turbulent Reynolds, you need the value of, please remember,
Roughness.
the roughness, correct. So the epsilon over D should be known. But if it's not known, you can assume it's smooth pipe, yeah. Just use the lowest graph. Then you can calculate EF. After you get EF, you put it into the Bernoulli equation, then you get the value of PB. I won't ask you to do it now because it will take some time. Just try it by yourself. Okay, any question until this part? It's basically just calculating EF. EF is based on the friction factor, Reynolds number, velocity, right? And then EF value should be used into the Bernoulli. Just make sure you choose 2 points which will help you to calculate, which will help you to be put it into the Bernoulli equation. Okay. Last part. Last part is, still remember, right? When you have liquid, yeah, flowing into the pipe, depending on the size of the pipe, yeah, depending on the diameter of the pipe, and depending on the flow rate, yeah, how much the liquid, then at some cases, the liquid, it won't fully fill the pipe, yeah. If the liquid is not fully filled the pipe, then you will need to calculate what we call equivalent diameters or hydraulic diameters. Or for other cases, when the cross-section area of the pipe is not a perfect circle, yeah, then you have to calculate the equivalent diameters. Please remember again the formula of equivalent diameters. It will be 4 times of the cross-section area. The cross-section area is the area of the liquid, not the cross-section area of the whole pipeline. Yeah, it's only the cross-section area of the liquid divided by the weighted parameters. Just remember, please remember, yeah. So this one is cross area of the liquid. And this is the weighted parameters. So for this figure, the cross area is only this part. The weighted parameters is the length of this part. Okay. If you already know the value of the equivalent diameters, you use this value of the equivalent diameters to calculate the Reynolds number. And from this Reynolds number, you can calculate the friction factor. So the friction factor calculation for this kind of case, for non-circular pipes or for a liquid that's not fully fill the pipe, then the calculation of friction factor should consider the equivalent diameter. That's the first. The second one, for the non-circular pipes, you have what we call this one, correction factor. Yeah, correction factor for non-circular pipe. Yeah, it will be depending on the the area, the shape of the cross-section area. And then this friction factor, yeah, this friction factor is the one that you get from this equation, has to be multiplied by the correction factor to have the corrected friction factor. Yeah, so the FF is based on the Reynolds number, but the Reynolds number comes from the diameter equivalent. Yeah, now this correction factor or non-circular factor will be the function of size and cross-section geometry of the pipe. For example, this one. Yeah, this is the rectangular, yeah, the left one. Yeah, rectangular, so should be have certain value of height and width. So the correction factor, yeah, the friction factor for it means the correction factor, the KNC, the constant for non-circular, is only based by the geometry. So then you do not see how much the liquid filled the pipe. From the correction factor, just see how much is the height, how much is the width, then you use this one. But it will, the velocity of the, so the correction factor will be influenced by the type of the flow, the regime, the flow regime. So for the rectangular pipeline, if the flow is the laminar, then you use this equation. If the flow is turbulent, you use this equation. For other types, for example, for the annulus type, then you can use this equation for the laminar and the for turbulent. Or maybe for the pipeline, so this is for the special shape of the pipe, then we have a special formula to calculate KNC, the correction factor. Okay, don't forget, from the KNC, you still need to calculate this one. Yeah. Yeah. KNC you get from the formula, FF you get from the Reynolds number, then you multiply it to become this one. And the EF should be this one. So the friction factor that you put to calculate EF should be already the result of this multiplication between the correction factor and the friction factor. Oke, any question? Ya, jadi Anda perlu hitung 2 kali ya. Jadi kalau pipanya itu bentuknya tidak bulat, ya, Anda perlu hitung 2 kali terkait friction factor. Friction factor yang awal itu dihitung dari diameter ekivalen. Dari diameter ekivalen dapat Reynolds number, dibaca di kurva dapat faktor friksi. Itu FF. Lalu dengan melihat bentuk pipanya, Anda ngitung KNC. Dari KNC Anda kalikan dengan FF tadi. Dapat FNFC. FNFC ini yang digunakan untuk menghitung EF. Kalau pipanya bulat, sempurna, KNC-nya 1. Jadi tinggal memperhitungkan yang FF-nya saja. Okay, any question until this part? Okay, now we go to the last part of the slide. We won't solve the equation, but I will guide you through how to do the equation. Yeah. So first, the case is natural gas. It will be transferred from Sengkang to Parepare. So different city. Yeah. The gas comes from the well production flow rate. Yeah, and the flow rate is quantified. Yeah, later as the chemical engineer, you must familiarize yourself with these units. Yeah, It's MMSGFD. Okay, now I'll give you some times to Google what is the meaning of MMSGFD. Not only the abbreviation, but what is the condition to calculate the flow rate. Okay, please check from the Google and then open your mic and tell me. Apa itu MMSGFD? What is the meaning? Hello?
Is it million standard cubic feet per day, sir?
Million, yes, it's correct. The abbreviation is correct. Million standard cubic feet per day. But please remember, this is gas, yeah. The properties gas, yeah, the density will be influenced by the pressure and temperature. So you will have standard. That's why we have standard term in this unit. Can you check what will be the pressure and the temperature from this standard condition? When you count the flow rate of the gas in MMSGFD, it should be referred to certain pressure and temperature. Coba dicari berapa tekanannya dan berapa temperaturnya.
Sir, is it 14 point, ada dua nih, 14.73 PSI?
14.7 PSI, and then the temperature?
Temperature is 60 Fahrenheit.
Yeah, 60 Fahrenheit. Yeah, this one. This is the condition for standard for the calculation of MMSGFD. Okay, the unit is cubic feet per day. So you can convert it into cubic meters per second, yeah, for the standard unit, for the SI unit, yeah, standard unit. Then, however, this one, from this exercise, you can see the well production flow rate is 50 mmSCFD. But the the natural gas will flows from Sengkang to Parepare, which is 300 meters higher. Yeah, Sengkang is 300 meters higher than Parepare. The length is 70 kilometers. The molecular weight of the gas is 70. The condition of the flow is 30 degrees C. Yeah, this is the temperature. This is the pressure. So from MMSGFD, you can get cubic meters per second, right? But this is the condition from the well. Yeah, the 14.7 and 60 degree Fahrenheit is the condition in the well. But condition at the pipe will be 30 degrees C and 60 kilogram force per square centimeters gauge. Yeah. So you need to convert it into Pascal absolute first. Yeah, you need to convert. It means you need to do conversion of the flow rate. Flow rate from the well, you have to convert into the flow rate in the inlet. Why you have to convert? Because the condition is already changed. At the well is 14.7 and 60 Fahrenheit. Yeah, the calculation of the flow rate is at this condition, but at the gas, at the pipe inlet, the pressure and the temperature is already different. So you have to convert it into the flow rate. You have to convert it into this condition. Using what? Using ideal gas. Ya, bisa ya. You just check from the earliest slide how to convert the value of the flow rate. Okay, now you need to determine the gas outlet pressure, yeah, at pare-pare, yeah, at the end, using 3 difference of pipe. So basically, yeah, after you get the value of the flow rate, yeah, from each diameter, yeah, because you have 3 types of diameter, yeah, you can use this one, right? And then you can calculate each of Reynolds number, yeah, when using different pipeline, and then you get friction, right? Okay, and then you have EF. Then you have P at pare-pare. Yeah, when you're using P5, when you're using 5, 10, or 15 inch of the diameter. Without calculating the number, yeah, without calculating the number, which diameter that give you the highest pressure at the outlet or the lowest pressure at the outlet?
Is it the lowest diameter will produce the highest pressure, sir?
The lowest diameters will produce the highest pressure. Why? Which one that will give you the biggest friction loss? Remember again, EF is 4L per D, FF, this one. Which one will give the highest EF?
Is it the one with the highest diameter, sir?
The one with the highest diameters? Why? You can check from the formula, right? Just remember again. The first, you need to imagine the shape of the graph of the fanning friction, yeah, or the Moody friction should be the same. In the laminar, it will be straight, right? When the FF is decreasing, and then in the turbulent, it will be decreasing throughout the Reynolds number, but until certain position, the friction factor is constant. Ya, kalau RA-nya sudah tinggi sekali kan, faktor friksinya konstan. So the one that matters is only the velocity. Increasing the velocity means you are increasing the EF because it's proportionally linear, right? Yeah, quadratic proportionally linear. Yeah, it means pipe. So it means pipe with higher velocity will give higher pressure loss. You will get higher velocity with small diameter or bigger diameter. Kecepatan linear itu akan lebih tinggi kalau diameternya kecil atau besar. Diameter pipanya. Kalau laju alirnya sama ya. Ketika laju alir volumetriknya sama, ya, this one. Which one is higher? U5, U10, or U15?
5, sir.
5, yeah. So smaller diameters will give higher velocity, and then it will give higher EF, higher friction loss. If you have higher friction loss, it means at the end, you will have higher pressure or lower pressure.
Lower, sir.
Lower, yeah. It means this one, U5 is the highest, but PE5 is the lowest. Oh, not this is Reynolds number, yeah. This one, this one is the lowest. What does it mean by lowest pressure at the end? Can somebody imagine? Basically, you still want the gas should have enough pressure, right, at the outlet, because maybe the gas will be used for other purposes. Or if you really have, for example, I think, but you need to calculate exactly the value, right? Maybe if you have smaller diameters, yeah, since you have smaller diameters, you have higher energy loss, you have bigger pressure drops, right? Higher energy loss means bigger pressure drop. Maybe at some point along the pipelines, the pressure reach zero. The pressure reach zero means the gas is not flowing anymore, right? Or maybe you have negative pressure at pare-pare. That's you don't want. So if to because this scenario might be happen, yeah. How to avoid higher pressure loss? You use bigger diameter, right? Yeah, you use bigger diameters means you use lower velocity, lower Reynolds number, and then you will have higher pressure at the end because the pressure drop is lower. Paham ya? Kalau tadi diameternya terlalu kecil, kecepatan linearnya akan sangat tinggi. Kalau kecepatan linearnya tinggi, EF-nya akan sangat tinggi. Kalau EF tinggi, delta P-nya juga akan sangat besar. Nah, kalau delta P-nya terlalu besar, bisa jadi di tengah-tengah itu P-nya sudah 0 gitu kan, turun-turun terus ya. Delta P itu kan menyatakan penurunan tekanan. Delta P shows you the decrease of the pressure along the pipeline. So, if the delta P is too big, then at some point the pressure might reach zero, the gas is not flowing. To avoid this, you have to change into the bigger diameters. Okay, but what will be the drawbacks? Or what will be the challenge if you are using the bigger size of pipe? From the price point, it will be more expensive, right? Bigger diameters of the pipe means, yeah, you need more materials for the pipe. Yeah, I think pipe with this bigger diameter will cost more. And it will cost even more when the size, the length of the pipe is very, very long. 70 kilometers is very long, right? Yeah, if it's only 1 meters, 2 meters, maybe the differences in price is not significant. But if you need to install 70 kilometers long of pipe, then the price of the pipe will be significant. The price difference. So I hope you can sense the differences here in technical or in the reality. Yeah, you have the trade-off. Yeah, if you go with bigger diameters, it means you need to invest more for the pipeline. Yeah, because the pipe is the cost of the pipeline is higher. To reduce the cost, you need to reduce the diameters. You need to use smaller diameters of pipe. But smaller diameters means the risk is to have higher pressure drop, have friction loss. Okay, that's why I asked you, please convert it all into the standard unit, yeah, to SI unit, yeah. The pressure should be in the Pascal. Be careful when the unit is still engaged, so you need to convert it into the absolute. Okay, and then the cubic meter per second of the gas should be converted from the SGFD condition, yeah, the pressure and the temperature at the standard condition, to the 30 degrees C and 60 kgF per square centimeters. Then you can get all the value. You can calculate the pressure at the end. Okay, any question? Then you can see how much is the pressure at the end by using three size of the diameters. Okay, that's all. Any question? Okay, if you have no question, I hope you can understand the concept. You can familiarize yourself with the calculation, with the formula, the steps of the calculation, and I hope you try by yourself. Not on the exercise, maybe not only in the slide, but maybe from the textbook, or maybe from the prosol. Yeah, redo the prosol, then do the exercise. Okay, to help you more understand about the concept. Okay, let me stop recording.